Bismillah ar-Rahman ar-Rahim. So this is laser diffraction and interference experiment, or light diffraction and interference experiment. We will start with a video that will explain why light will diffract and interfere.
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up, peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere, and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having two drops of water fall in a swimming pool.
That's right.
Exactly the same
and then
pattern.
They go and overlap. As this ripple overlaps with those ripples, down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, then a dark spot, then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah,
that's because
burgundy.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference between red and
so
blue...
that red bin over there and the green part is just, I'm seeing
it's
that, and it's just different wavelength.
length.
And that's how we bring in all these beautiful colours all around us.
Exactly.
طيب إذا شفنا الانترفيرنس diffraction of the white light، وزي ما احنا عارفين الوايت لايت تكون من مجموعة من الألوان، كل واحدة ويف لينث، فبصير diffraction وبصير interference، بس كل ويف لينث إلها مسار، إلها ويف لينث مختلف، فبصير لها مسار مختلف، فبصير عندنا bright spots زائد dark spots بس للألوان كلها. عشان نتجاوز المسألة هذه، احنا استخدمنا في التجربة تبعتنا استخدمنا ليزر لايت. So we start our experiment with a monochromatic source of light، يعني لون واحد، عشان نتفادى انه الالوان تتشتت ويطلع لنا اكثر من بقعة. هون أنا حطيت اللون أصفر، في التجربة تبعتنا ليزر ولونه أحمر. We will put a slit in front of it, so it will prevent light from going to the other side, only through these two holes, hole 1 and hole 2. And we put a screen so we can see the interference pattern. We can measure the distance between the slit and the screen. It's important to measure it. It will come into our calculation. And then we put our observer looking at the two holes from this angle. So he is looking at this X point. So we start with ray 1 from the top opening in the slit, and then we introduce ray 2 from the bottom slit. And here realize please that the length of the green ray is exactly as the length of the blue ray, and clearly there is a path difference. There is a path difference. يعني from here to there we need to add a longer piece of the path, and the path difference is the key to all our derivations. We can also measure the y distance. It's between the first interference, bright interference, and it's the distance between the first bright interference and the middle dot of the laser. Now let me remove y and L, so we can just add more diagrams. Now look at this. We call this theta. We call this theta. It's the angle between the blue ray and the horizontal. Let's do some calculation and let's focus on this area now. Let's focus on this area now. So as you can see, this is theta, and here it's a 90-degree angle. That means this angle, let me remove the square so we can see, this angle is 90 degrees minus theta, because the whole thing is 90 and this is theta, so this is 90 minus theta, and this is theta. This is theta. So let me remove 90 minus theta. So now this is theta, and we call the distance between the two holes, we call them D. We call them D. Now realize that, well, the path difference is nothing but D sine theta. D sine theta is really the path difference. And let me now take this opportunity to see if the path difference is equal to lambda, 2 lambda, 3 lambda, then we will have constructive interference. And d sine theta is equal n lambda. Let me explain that. So here we have two waves. The first wave, two identical waves. So the first wave at the top and the second wave at the bottom. So that's from the first hole, let's say, or the top hole, and this is from the bottom hole. Now let us realize that this is lambda, a length. Just in the sound wave, for example, it was 10 centimeter, 50 centimeter, 20 centimeter. It's just a length. For the light wave, it's much, much, much shorter, but it is a length. Now, when the two waves meet at that X point near the observer here, if they meet maximum with maximum, red with red, then they will add up. If they meet blue with blue, they will add up. So basically, you will see, or we will see a bright spot. Now, suppose that there is a path difference. What's the meaning of path difference? That means I will just shift my wave. I will just shift my bottom wave. So based on the path difference, for example, here, maximum with minimum, and look at the path difference. The path difference, that means the difference between this wave and this wave is lambda over 2. So when it is lambda over 2, I will have destructive interference, maximum with minimum, red with blue. I will just kill the light, and that is the dark spot. That is the dark spot. We can't see anything. Now, if we keep shifting our wavelength, or our second wave, if we keep shifting, and the shift is lambda, you see this is the shift. So I shifted, or the path difference is lambda, then I will have constructive interference. This is lambda is equal 1, 2 lambda, 3 lambda, etc., etc. So we go back here again. Let's read it again. If the path difference is equal to lambda, 2 lambda, 3 lambda, then we will have a constructive interference. A constructive interference. So let's move down and see. So our equation here at the top here, d sine theta is equal n lambda, d sine theta. Here, when theta is small, then sine theta is equal tan theta, and what is tan theta is nothing but y over L, y over L. So finally, we come to the equation that will apply to our experiment. D, the distance between the openings in the slit, is equal the y, the distance between the spots, and n, that means the first bright spot when n is equal 1, the second bright spot when n is equal 2, the third bright spot when n is equal to 3, and n is the same variable in lambda. So when n is equal 1, then dy1 over L is equal 1 multiplied by lambda. When n is equal 2, then d, we look at the second spot, and we divide it by L, and we multiply it by lambda. And you will realize very fast that the distance between the origin and the first spot, let's say it's 3 centimeters, we will find that the distance between the original spot and the second bright spot will be 6 centimeters. So it's doubled. We double the distance and we double n here, so they will just disappear. They will just disappear. So basically, the equation, if n is equal 1, is just d, the first distance between the origin of the laser and the first neighbor, that's the distance, divided by L, and it's equal to lambda. Thank you for your time.